there were
I didn't get a
in the
chance.
past few days, you know.
Yeah, I didn't get a chance to look at them. Nope.
Okay.
I don't know.
All right.
I'm hoping that after this workshop, we'll have a lot more people that are trained and more falls can get looked at. That's the goal, I think. Yeah. All right, so we're streaming live on YouTube. I don't know if you got a notification of that, but it seems like it's working. So be 9 o'clock here in just a minute, and we'll get started.
Okay. No word from Sammer.
Okay. Well, Pat's not here yet either, so we'll give it a minute. I'll have to prepare some music next time for the waiting period. Some Jeopardy music or something. Hi, Steve. Welcome.
Okay, Sammer says he's joining.
Okay. Yep, I see Pat's joining too. I think we've got everybody coming together here. So it's a minute after 9 o'clock, so we'll get started. Welcome everyone to the Strewnify Doppler data analysis workshop. We're gonna jump right into this. I think we're streaming this on YouTube, so we're gonna throw a lot of information at you, and if you miss anything, we can go back later and watch it on the recording. So I'm going to go around and look for introductions. Anybody who wants to introduce themselves. We'll start with the presenters, I think. Tony, you want to introduce yourself?
Okay, yeah, my name's Tony Licata. I'm in the Detroit area. I live in the Hamburg meteorite strewn field, and found a couple meteorites those years back in 2018. And so I'll just give a few tips on how to open the tool and do some basic stuff. So hopefully that helps some of the beginners out there. And yeah.
Thanks, Tony. And I should introduce myself too. I'm Jim Goodall. For those of you who don't know me, I am the author of strewnify.com, and I've been doing this since 2018. So I'm not an old pro at this, but I've been working mostly on my computer simulation. So I do simulations of meteorite strewn fields and trying to get the information out there so that meteorite hunters can be successful. So that's the goal of Strewnify. Let's see, Pat, you want to introduce yourself?
Pat Branch, been hunting meteorites for a long time. I also used to be a radar engineer for the Joint Stars, and so I knew a lot about radar when I first started actually looking at the Doppler data. And that was pretty much around Ash Creek time when they first realized, hey, Doppler could catch these things. I've also analyzed seismic and video and the satellites data. So
thank you. Yeah, Sammer, you want to introduce yourself?
Sure. I'm Sammer Hariri, and I'm a geologist by profession, and I enjoy the scientific aspect of the meteorite hunting endeavor. And tonight's presentation about the weather tool is also a fascinating topic for me. So looking forward to it.
Cool. I'm not going to force anybody else to introduce themselves because I didn't really tell anybody we were going to do that. But if anybody else wants to introduce yourself, go ahead.
Hey, I'm Steve Ansari, and thank you so much for inviting me to this. I work at NOAA's National Centers for Environmental Information, and I just got off the road from a 6-hour car drive back from a soccer tournament, and just thrilled to be able to join. I'm the main author on the WCT on the Weather and Climate Toolkit, and have worked to help make radar data more accessible out of the NCEI, which is like the archive of all the weather radar data, and absolutely thrilled to see what really novel things everybody's doing with this data and with the tool. And this is exactly why we made the tool, and try to get the data on the cloud, and just to make it more accessible and allow people to do really awesome stuff with it. So thank you so much for inviting me to this, and can't wait to see how you guys are using the data in the tool. That's just awesome. Thank you.
All right, great. Thanks, Steve. We are certainly thrilled to have you too. Anyone else? All right, let's get started. We probably have a lot of material to squeeze into the time we have, even though we have 2 hours. So go ahead, Tony. I'll let you go ahead and start sharing.
Okay. And hopefully I'm sharing. I don't see.
It says
Oh, hang on.
I'm sharing. Let's see. I think there's one more step. You have to click share after the.
Okay.
I made that
Share
mistake before
screen.
too.
Okay. And
I'll stop sharing in case that stops you.
all right. So share screen. There we go. I think you needed to do that. That's all right. And I will share my screen. All right. So I'm just going to open the tool and show some basic functions of the tool. I'll leave the experts who are here, including Steve, to go over the more complicated. I also have some questions, some things that aren't working for me, and hopefully I'll demonstrate those as well. But I'll be very quick and then turn it over to those who know more. Okay, so like I say, I found meteorites in the Hamburg strewn field using Mark Fry's data, Doppler data, and so I became interested in this tool back then. So here's what you have here. Open it up. This is what it looks like. And the first thing to do is open up the layers. You want to know where these Doppler sites are across the country. We'll be looking at the Hamburg Fault. So over here, we want to see what stations are available, Detroit area. And so you can hit the NextRad sites, and that shows you where all the stations are. And if you want the labels on them, there you go. You have all the various Doppler stations. So the one that turned out to be closest to the Hamburg Fault were these two, and we're going to use the KDTX because that actually shows hits. So you can close that down. You can do other things here where it says dark up here in the corner. You can say, let's see. Oh, I've got pictures in the way I can't see it. That's weird.
You can grab those pictures
There.
and move
Yeah.
them, I think. Yep.
Yeah, I want those out of the way. There we go. So let's change it to a map. We'll go streets. So let that load. And so here is the Brighton area where I live. And so I've already got KDTX. We knew that one station near us was called KDTX. You can hit this arrow and there's all those sites that came up on the map. So we're looking at KDTX. And I've wheeled the date back to 2018. I don't know of a fast way to do it other than just keep continuously clicking these arrows to go back in time to look at historical falls. But that's what I did. Just clicked it a million times and got back to January 17th, 2018. And what we're going to do now is list files. And it brings up all of the all of the radar data for that day. And we know the time of this fall was around 110 or UT, 110 UT. So that's right there. So you look at the timestamp here. This one's 107, a little bit before. And so that's the one that, as it turns out, produces hits. But you can actually shift click all of these and bring them in as well and animate those. But first of all, let's load that data. So that brings up this window. Oh, and I forgot to reset. I forgot to uncheck the reset zoom, so it zooms back out. So if that happens, just uncheck the reset zoom and you can keep it where you had it zoomed in before. So we can knock this down for now, let it refresh. And here we have all the radar data for that day. This is at 047 elevation sweep. Now, as you go down, we'll load this sweep. You can see it's fairly noisy. And we'll go higher and higher. And over here, you can see the time that that sweep took place. If you can see my mouse, can everyone see my mouse? Can you see the,
Yes,
the
we can see
cursor?
your cursor.
I can,
People see-
yes.
You can? Okay, so as I point to things, you'll be able to see that. So over here in the upper right-hand corner, you have the actual time of that sweep. So 148 represents a 107.28 timestamp. And we're not seeing anything that that looks like meteorites. Plus there's a lot of noise. I'm not sure what that was. So we go a little higher and load that. And there we start to get some hits over Bass Lake and Strawberry Lake. Okay, so the other thing you can do before I go on is you can not do it this way and just go right to, say, 3,000 feet, 3,000 meters, and load that. And here's some more radar hits of meteorites for that event. And so as you go to different altitudes, you get a different signature showing up. These hits are just some noise over at Portage Lake. You can go higher and see if there's anything else. And there isn't. So it turns out above that, there weren't any. So, but back to the elevation, we can bring this back down to 0. And here's where my questions come in for the experts. So we just load that again. So we know that the hits start showing up at about 248. So let's load, so I want to send these out. So what you would do at this point is data, right? And we're going to animate. And I like to send them out separately to Google Earth, right? And so this was the way to do it, but it's not working for the Hamburg Fault. It was working fine for the one recently around Grand Rapids, but it is not working here. So you say export KMZ, start. And I want the current sweep. What I found, rather than loading the full volume, which gives you all the noise and everything in one big lump of data, and you're supposed to be, when you do that, you're supposed to be able to use the time slider, when you'll see this in a minute, in Google Earth, but it's not working. So we can say full volume, or I can just do current sweep. So I landed on just doing current sweep, but as it turns out, that's not working either for the Hamburg Fault unless I do it a different way. So I'm not going to waste any time. Just trust me, that doesn't work. It gives me more like the lowest sweep. It doesn't give me the current sweep. So that's just one thing I wanted to point out. So I'm going to cancel out of here without doing that. And the workaround that I found to make it give me the current sweep is I just go over here to the right where it says save KMZ, and you get the same window, but this time when I say current sweep, We'll turn the shadow off, drape on actual radar, and we say, oh, we're going to browse out here. And so this is my Hamburg Fall folder. And so this is elevation 248. Elevation 248 would be my file name. I'm just going to overwrite that one. Okay. Say yes to that and say go. Yes again to the overwrite. And then it asks to open the file, and it opens Google Earth. This is exactly the same thing that would have happened had we done the animate. And then it brings your file into Google Earth as a temporary places. As you can see above the temporary in my places, I have all of the elevations that produced hits already loaded in there to save time. So this one is elevation 248. You can see it right up here. So that's already loaded in there. So we'll just turn this one off. Okay. So what I do is I load them. I go through that for each elevation that's producing hits. And then when I get into Google Earth, I can turn them on and off. And here you can see, let's see here. Find the right place. There we go. There's some hits. So you can really sort out the data this way. And these are 4 separate files that I saved individually. You're supposed to be able to say full volume, and then you come up here and use this time slider. But for me, when I do full volume, it doesn't work. So those are my questions. So I landed on this way to save them out all as separate files. And it is kind of nice. That's all I wanted to show is you can turn them on and off and the elevations show up. You can see the difference in the height from ground. So you can see where the hits are occurring relative to the ground. So that's kind of nice. But I would like a quicker way to do it so I don't have to load all of these individual files. But as it is, and my other question, why when you hit animate, if you want, I can demonstrate that, how it doesn't work. All right. Should I do that, Jim, or should I stop here? You on mute?
Yeah, can you hear me now?
Yeah, I can hear you.
Sorry. Yeah, I've had intermittent issues with full volume scan too. And I found in some of my testing, I think sometimes it's Google Earth's fault. I'm not sure if it always is,
Yeah,
but
okay.
like I'll close Google Earth and start again and open the same file and I'll be able to see it. Because sometimes I'll get an empty file or what appears to be an empty file. And then when I reopen Google Earth, it works. But I don't know if that's always the case though. It's been sort of intermittent.
But just to repeat, what I was getting is when I hit animate.
Yep.
Let's just do one, okay?
Yeah, demonstrate the issue. That's we got time, I think.
Let's just do one. I'll hit animate. And first of all, wait, before I hit animate, let's show you what it should look like here in the tool. Turn this off for the time being. If I load the, let's say the 346 sweep, I can see some hits here. Let's get more hits. Load the 443 sweep. Okay, timestamp is, and this is important, 10728. Okay, so we see some hits showing up over Hamburg Lake, where we actually did find meteorites. So I want to see that on Google Earth now. So I'm going to go to data and animate, and this is how it's supposed to work, but doesn't. So export and start. And we're going to say current sweep. right? As opposed to full volume, and I'll demonstrate that next. For now, we'll do the current sweep because this doesn't work either. We'll give this a name. We'll call it test. All right. And save that. Go. And it's loading. Yes. So it brings this in. And
Oh, you've
let's
got
turn these other ones
data.
off. We'll turn these. Yes, you get data, but but this is not the right data.
Oh.
This is not the right data. It's not at all what it looked like. So we have our, let's turn the other stuff off. Let's turn this.
Yeah, you're obviously getting the
off.
lowest scan, it looks like.
Getting the lowest scan. That's right.
Yeah.
Exactly right, Pat. And I loaded a specific scan. I wanted the scan that was producing the hits, and that's not the one. And so that's not working in that case. So let's go back to the tool. So I got the lowest scan instead of going back to the tool here. Instead of the 443 scan, it looks like I got the 047 scan. And I went through this, trust me, each one of these produces only the 047 scan. So that's all you get. You don't get the scan you're asking for. Secondly, if you do say 443 again, animate, export, start, and you say full volume, right? We'll do this test 2. You should get a full volume, and I think that's working, but the time slider doesn't work. And that's kind of important if you're going to sort through the data. Once it's all in one big blob on Google Earth, you're going to want to weed through what you want to see, and you can't do that if the time slider isn't working. So I don't know what I called this now. We're going to turn this off. Okay, it's called export. So this is what comes in. And no, actually, I think even this one is just that first scan. It's not even the full volume. And that explains why the time slider doesn't work, because it's only one single timestamp. So the animate tool is not working for the Hamburg fall. However, I showed you my workaround that does work. If you go back here, the workaround was to go over here to the right and say save KMZ that way, and any way you want to save it, it's working. So just wanted to point that out. It's a minor inconvenience, but and by the way, this worked for every other fall. It just doesn't, well, every other fall I've tried, and it just doesn't work for this Hamburg fall. So I think it's a bug or something. It could be Google Earth, like you say, Jim. But it's no big deal as long as I find some way where it works. And my main point was to, if you can get the full volume scan to work, it's a kind of a nice way to look at the data once you're in Google Earth, and you can use that time slider. Maybe someone else can demonstrate that. Like Sam or
Anthony, go
yes,
back
sir.
to your Google Earth for a minute.
Okay.
And let's page on the left-hand side where it says
Mhm.
image frames, page down right there. And then open image frames wider. That little checkbox on next to image frames. See image frames?
Oh yeah.
No,
yeah.
not that one. That one. There you go.
That right there.
Yeah. Now,
So,
another bug I've seen, and that's probably what you're running into, is that, see, because you have all the scans there, you can turn them on and off. So you have all the scans in there, turn them all off, and then just turn on, the 4.43 one if you want.
oh, okay.
So you're
That's
getting all the
interesting.
data.
So where's so here's the 443.
Right.
Let's
So you
turn
can
that
just
one
click on that one
And
and
it
see.
should be. It
Should be
should
that
be,
fall.
there it is. Oh, okay.
Yeah.
So they
but
are
what
all in there.
happens?
I just didn't
Yeah,
see
what
them.
happens is when you import another radar set on top of a radar set, if
Mhm.
they overlap, only the most recent one will be visible. So it's probably loading all the data, but it's probably, the last one visible is the bottom one for some reason. So you're only seeing the one, even though
Okay.
all the data is actually in there. So
Well, that's great.
So turn them all
That's
on.
exactly
Tony. Does
what
it,
I was hoping someone would show me what I'm doing wrong there, and that was it.
And it works as you start like checking them now.
Yeah.
Yeah.
Okay, so
They'll
if you
start
open image
overlapping
frame-
and stuff like that. You get this and the other methods too, but like
So
I say, I
what's
just click them
weird-
off and click them all back on. But if you reload it, like you've saved it as export. Now, if you go out and close export and reopen, or if you just reopen it in Google Earth, it will display properly.
So here's a question. I exported over here, I exported current sweep. And what I got over here under image frames is I got them all. So
No,
why-
you exported full. When
I
you
did?
did this run, you said full sweep, not just the current one. Test one did the current sweep.
Oh, okay.
This export that you just ran, you selected full sweep.
So
And
that
because you
was
were
the
showing the
volume.
time slider doesn't work.
Yeah, and so, okay, back to Google Earth. Let's see that. So the time slider will work if I turn them all on? Will it work?
I don't know. I'm not sure. I don't really use the time slider, but
No, it's not working.
no.
So
Now the
that's
time
still not working.
slider.
But this worked before. I know I've made this work, but it's not
Yeah.
working for the Hamburg fall.
hey,
The time
Phil-
slider is more for the Google Earth image underneath for all the times previous to it. But if you now reopen, just go up to File and say Open. In Google Earth, go up
back
to
at the-
File, Open. No, in
Oh, in
Google Earth,
Google
not in
Earth, okay.
WCT.
File open, yes.
File open, export. Whatever folder you just saved that file in, export in.
Oh, where do I keep it? Oh, it's gonna be.
I don't know.
I'm
Documents,
talking to myself,
meteors, that's where I keep
users,
mine. Documents,
Anthony.
meteors.
Meteorite, Doppler research, Hamburg fall, that's the folder.
Export is very top one, the very top one.
Yeah,
Double click that.
yep.
Now, it should have asked you if you want to close the current export and reopen this new export, but
Oh,
now try
Well,
the
it's
slider
only if
bar
it has the
after.
same name.
Yeah, well, it's usually asked me to, you want to
slider
close
bars.
it.
Slider
It's
bars.
still not working? Okay, I
Still
just
not
wanted to see if that changed it, because,
No, I haven't been able to make that work for this fall.
yeah, for me,
As
it
I was-
does
as I was
reload it
looking at
and shows all the data at least,
It
where
does. and
previously you don't
that's-
see all the data.
That's really good. So I can say full volume now, and then I can turn on, then I don't have to load them all as individual files. Anyway, that's all I wanted to show folks is, how to open the tool, how to display the stations, and figure out what the nearest station to your fall is, and then load that station, and then export out the hits that produces as you go through the various. Now there's a lot more you can do here. You can show radial velocity. Pat, you talked about something where if it shows up red and green in an area, I'll just quickly show radial velocity because that's kind of cool. This is something I just learned from Pat. When you say radial velocity on this sweep that's produced this sweep that produces hits, and we load that, gives you this kind of, well, that's not so much red and green. Let's try this one. But it shows the turbulence is what you were saying. So that's green, that's red. So that's kind of a good indication of meteorites, Pat was saying in our last chat. So at any rate, so there's a lot more you can do in here as you analyze the data. I would really like to understand what all of these things are, but I'm no expert. But the first thing you do, it comes in by default, it's on reflectivity.
Yeah,
I'll
most
let
of you won't understand. Correlation coefficient is the correlation between the reflectivity in one phase versus reflectivity in the other phase. These are dual polarization radar now. So it sends out one wave that's horizontal to the ground, and it sends out another one that's vertical to the ground. So, you know, one looks like a snake crawling across the ground, the other one's up and down against the ground. And then it compares the returns of those two and gives you a number for that. And a perfect correlation is 1.0. You know, if you get the exact same energy in both those phases, then you'll get a 1.0. So that's what correlation coefficient is. Meteors, if they're perfectly smooth around, this gives you a good indication of the shape of the meteor. Okay. Because you'll get a different reading between them. So, but a perfectly smooth round ball should return a 1.0 anyway. But you know, you get
that'd be red, right? Red or pink.
Yeah, whatever.
According to this graph, if everyone can see the graph on the
right.
Yep.
And then
legend.
Yeah, typically it would say, oh, that's a nice round meteor. If you're getting the around the red, around 1, you'll get a nice round meteor. If you get something in the 0.8 or something, then you might question whether it's even a meteor, but it might be a square meteor or a very odd shaped one. So
yeah,
differential phase is very similar. It just looks at the phase instead of the reflectivity. So it's the difference between the phase of the vertical polarization versus the horizontal polarization. Differential, the other differential magnitude, right? Look at the other products. The one right before CC is differential reflectivity. That gives you the magnitude difference rather than the correlation coefficient. That correlation coefficient is a Peterson's correlation coefficient if you're into statistics, so you'll know how to calculate it. It's not so hard. Okay. But then the other products, the spectrum width is basically it's a bandwidth, and I think you get spectrum width from the single phase. I think you used to get spectrum width before it became a dual polarization. Steve can probably tell us for sure. But the spectrum width is basically how wide the bandwidth of the returned reflectivity. So how much it's changed. You know, it's sending out at 2.401 gigahertz or whatever. And if it says, okay, my bandwidth is 0.1 gigahertz, then you're getting a really wide band on it. You're getting a spread. Something's changing the actual phase or actual Doppler of the return. So, and then the velocity, of course, is velocity with respect to the radar station, whether it's the object is moving towards the radar station or away from the radar station. So it's an actual Doppler difference between them.
Mm-hmm. Oops, I don't want to zoom. So as you were saying a couple days ago, if it shows up green, it's here on the negative side, and if it's kind of in the red range, it's on the positive side, which kind of means they're both sides of zero, which means there's a turbulence going on there. That
typically
find that it's meteorites. That's the kind of real world explanation that means something in terms of, you know, whether these hits we're seeing on the screen are potentially meteorites on the ground or not.
Right.
The technical stuff of what all of this other stuff is great. But like if I put it on spectrum width and I now see, you know, understanding all that you just said, I won't try to repeat it, but you know, does that mean anything in terms of, you know, these things are, I see green and pinkish now there as well. Does that mean, is that any kind of an indicator as to what these, besides raindrops, for example?
No, and spectrum width really doesn't give you too much.
Yeah.
Yeah.
So, and then differential
The differential
reflectivity.
reflectivity, the correlation coefficient, differential phase can give you some indication of the shape of the meteors
Shape,
that you're seeing.
okay.
But nobody's going to understand them, so
Okay.
probably not important to cover.
Anyway, I really like the radial velocity one. I'm going to be using that one a lot. And then,
Yeah, and we have to give credit to Mark Fries, of course, for that, because he's the one who really discovered that
okay,
they'll produce turbulence on the reflectivity product.
yeah, and I do see that that is very true with respect to the Hamburg fall.
Right. Once you see
versus,
that, you start,
some of the
you get in your
other-
car and you start driving. You
Yeah,
quit worrying about the radar and you go drive. Get
you
underneath
can
it.
see over here on the one side of the station, it's all green, and on the other side, it's all red, and the hits stay fairly consistent on either side of the station until you get over here to the Hamburg fall and you see both colors. And so the theory holds true. So I was happy to see that. At any rate, I'm going to give the floor over to someone else.
If I may add one thing about the velocity there.
Yes.
If the meteor is bigger, you would see more of a red and green. You know, right now it's not very red and green, that hit, but if it was a bigger meteor, it would create more turbulence, and therefore you would see more of a red and a green on the legend there. That's my understanding, at least.
Okay, let's see the hits over Bass and Zuki Lake here. Oh, they don't really show up too well.
Yeah, I'm not sure if the Hamburg one was a very big meteor compared to some others,
Right,
other
right,
examples
so-
where the velocity becomes very important to see that. Yep.
Yeah. Okay. Anyway. Thank you,
Hey, Tony.
everyone. Let's turn this over to the next presenter. I
Yep.
will unshare my screen.
Real quick, before I hand it over to Pat, I'm going to show the pretty picture we were looking at the other day from the Muskogee Fall.
Jim, I don't
Yeah.
know that your YouTube is showing up properly, so I just went and looked at it and I didn't see that it was
It
YouTube
did
is streaming.
earlier.
It says still waiting or something. Well,
I
to me
see
it
it,
says it's
but-
waiting, but maybe I'm hitting the wrong link or something. Or
I see it. I don't know. I'll have to check it later, I guess. I think it's working.
okay,
It says I'm live, but there's nothing else I can do, I guess, with that.
okay. Mine says waiting for Strewnify.
Okay. This is just the Muskogee Fall was one of the best 3D views I've ever seen of a meteor in Doppler radar. You guys can see my screen.
Mhm.
Yeah. I thought it was cool that you could see you can actually see the meteorites when they're still on the lit path of the meteor. I think you can
Man,
look
I
down
should have
too.
driven to Oklahoma on that.
Yeah.
I got friends there. I could have done it.
And this is the data Mark Breeze sent. So Mark Breeze did this analysis. He pulled in data from 4 or 5 different stations, I think, and put them all in one file for me, or for everybody. And yeah, it looks really cool. So this is the kind of thing you can get if you can get the full volume scan to work.
Yeah, that's
Yeah.
what I was trying to say, and I
Yeah,
can't get that.
and it's useful to have the 3D scan because you can look at, like this wouldn't be weather up this high, right? You can turn it sideways and say, well, that has to
Now-
be something besides weather.
For Mark Fries to do that, Mark Fries,
Yep.
would he have to do each station separately? Like he'll do a full volume for one station and then a full volume for another station, and then
I'm
bring
not
all
sure how he
three in?
did it. Yeah, you could do it.
I think you
You
would.
could do it different ways.
Yeah, he would have to
yeah.
do each radar station, but
Yeah.
he could load them
Yeah.
all through some script. He may run a script and load them, but
Okay.
I think he does it by hand
Okay.
and walks through them.
At any rate, when full volume is working, it's a really great, quick way to get results.
Yeah. Yep.
And
All
I
right,
was
I'm good.
just wondering if anyone could speak to why it might not work on the Hamburg fall. Is it because it's old data?
Well, your full volume scan did work. Why
Yeah.
the times slider doesn't work, I don't know, but
Yeah,
I mean, you got the data.
That's
I don't
true.
ever use
I
it
did.
that way. If I want to do a full volume download, I'd do it from straight from the front page. But
Okay.
yeah, it does have a problem that when you load one and you load another one and they overlap, the first one disappears, and only the latest one seems to show. But then if I go and save it as a file and then reload it, they all show. So
I was just wondering if maybe with respect to the Hamburg fall, it's kind of a legacy data kind of problem, and it has, and with
nah.
fresh data, that's not going to do that. Because it seemed like with fresh data, it works fine for me too, but not with this historical fall. Just curious.
And Steve, feel free to speak up. I don't know if we didn't hear you before.
Yeah.
Yeah.
First, thanks for pointing out these things for sure. It looks like there's definitely some sort of bug going on there. I'm actually grabbed my just booted up my work laptop. I'm on my personal on the Zoom to try to reproduce this and see what's going on. And I'm not sure yet. It looked from what you're sharing like maybe their altitudes weren't being represented correctly. They weren't separated. But I'm not sure. So I'm gonna dig in and see if I have the site and the date here, and I screen grabbed it and just so I can go in and try to reproduce that. So I'll
Okay, yeah, something to look at over time. I'm certainly not complaining. The tool is awesome. I think it's amazing.
Well, thank you. Well, you won't hurt nobody's gonna hurt my feelings if they're like, this isn't working or this could be better. This is the kind of feedback that's super helpful in finding bugs and also looking at ways to make things go faster. One thing you mentioned, I'll just mention it now, about the date thing. You can type in that calendar date field.
You can.
You can click in that and just type. So you can do like your month, day, like
Let me try that.
/month/day.
Okay,
Or
let's
month,
see.
day, year, I guess, whatever the format is.
Yeah, that was gonna be one of my tips.
Data, I can type it right in. Okay. As long as you use that format, right? Okay, I see it's working.
All right, we'll let Pat go ahead and start sharing. Keep chatting, that's fine.
Yeah, that does work great. Thank you, Steve. I'm
Okay.
not sharing
let's
at the
see.
moment, but it's working. I can get the next by typing in.
Our application I want to show. I show the
And I don't know if anyone else is checking the YouTube, but I can see it. I don't know why you
I
can't see
checked it and it still says waiting.
Huh.
What are you using to stream to YouTube?
Zoom.
Oh,
Maybe it won't show up until afterward. I'm not sure.
Till after you save it.
It says 4 people are watching. I don't know. That means 4 people are seeing. the
Well, they're
screen.
waiting. Mine says people are waiting.
Yeah.
If
All
you,
right.
if you
I
click
see
the
that it's
link,
working.
the link that's sent through Discord, it does work because I'm
Does it?
watching it on my cell phone and then watching
Okay.
you guys on my computer.
It's a different,
Okay, good.
it's a
I
different
did
link.
the
There it
one.
is.
Yeah, I did the one you sent through the email. I clicked on that one and it says waiting, but
I just shared the link in the chat for everybody.
okay. Well, now I have to go to the Zoom meeting to.
Yeah, I hope I didn't get 2 different links shared.
Yeah, there are different links between the email and the.
Maybe
I'm
Zoom does a
getting-
new link for every time you do a live.
I'm getting messages from other people saying it is working. So it's working for some people.
Okay.
I don't know why. Yeah, some. At
Okay.
least it's getting recorded. We'll be able to see it later, I think.
Well, I do data a little bit different than Anthony, so I'm going to cover the Junction City, the Georgia Fall in September. You know, from AMS, we kind of knew it was here, right around here in the middle of Georgia. In fact, AMS had it about 30 miles too far north, but if we just look at in general, okay, there's the closest radar station. I tend to not like the closest radar station, but you know, I do kind of like to try and get a couple of outlying radar stations. In this case, you got like, you know, 8 radar stations you could look at. You know, some are quite far away, but are reasonable enough to look at. And one reason I like to look at a far away station is because there'll be a lot less clutter. You know, if you can get something on a far away station with there's no clutter around, then at least you get the right area. You know, you'll know, oh, there's a hit there and it's not 30 miles north, it's really 30 miles south. So, you know, you can narrow down the area a little bit better. Also, there's so much clutter when it's really close that, you know, you can only use the highest 2 or 3 elevation scans that are decluttered to actually look for radar data or radar signatures. So, yeah, I prefer a little further away stations, or if the timing's right on a close station, then, you know, go for a certain scan of a close station. Now, in this case, we know it's very close to KJGX, which is one of the Air Force stations, Robins Air Force Base. And if we look at that data, I'm going to go to the NOAA tool. Can you guys still see my screen? I assume.
Yeah.
And what I do is I go through each one and I just download all those scans, you know, like KJGX, there was a 401 scan and then there was a 411 scan, so 10 minutes apart. So it takes 10 minutes to do that full volume scan. So I just download that full scan at 401. And then I always like to go typically one before and one after. In this case, I didn't. I just grabbed one afterwards because I like to look and see if there's a hit of some sort. And I'm wondering whether it's radar or whether it's rocks in the air, you know, if it's meteorites, then I'll go look at the later scan to see if that hit disappears or if there's a similar hit. And, you know, maybe moved by the wind, then I'll say, well, that's a cloud or that's a flock of birds or something else. It's not rocks in the air because they wouldn't be moving around like the clouds do. You know, they continue to fall versus, you know, clouds stay at the same place, the same altitude. So in this case, like if you look at the KJGX data, wait for it to upload, boom. Yeah. Now I happen to know that, the Junction City is right in here somewhere. And of course, the lower scans, it's just crowded. You can't really see any data there. Now, also from a video, one of the reasons I really like a timestamp of the event time, because it really narrows down what I have to look at, both the seismic wides, which isn't as bad, but for the radar data, typically it takes a meteor, 2 to 6 minutes to fall and hit the ground from end of dark flight. And so the time frame I want to look for in the radar is usually 1 to 4 minutes after the event time. I know the event time for Junction City was 4:04:50 UTC. So let's round that up to 4:05, since it's only a few seconds away from 4:05. So I'm going to look for 4:06 to 4:09 time frame, or maybe 4:10 time frame, typically. So anything that consistent that shows up before that time or after that time
Pat, we can't
is
see
not
your,
likely to be meteors.
we can't see your file list. I don't know if that's what you were showing.
Oh, that's okay. I moved it out
Okay.
of the way. So
Okay.
because I'm just going to concentrate on this one radar, the very first one I look at. This is the closest one, and I'm just pointing out that there's a lot of clutter. You're not going to find rocks in the air from this type of clutter. So the first 4 scans off this have too much clutter to see anything. Even the next scan, even if we're zooming into the general area. Now here's 352. That's the first scan. Hey, there's a dot out here, but is that just a random dot? And as you zoom in more, and I should be using my mouse. Let me go get my mouse. Now that first looked like it was only one little dot, and one little dot I would probably ignore, because one little dot's just a random hit, if I don't have something else better. But it turns out when you zoom in, this is 5 hits in a back to back. So it's 5 range bends deep. So that gives me more interest. So if I saw something like that standing out on its own, away from everything else, and you still you see that in spurious stuff too, because here's another one, and that's why you have to look at multiple radar, and hopefully it shows up in different scans. In this case, we'll go to the 448 and it disappears. So did these random ones down here. So from a close radar, if that's the only one I looked at, I would say, oh, that's probably just a spurious hit, and I probably wouldn't pay much attention to that, especially if I looked in the velocity data for that scan. Now there, once you look at the velocity data, you say, hey, that's probably rocks in the air, because I got red and green next to each other, and I've got strong red and green next to each other, plus 70, minus 70. So, that's a good indication there's rocks in the air. But that's all you get from the close in radar. If that velocity disappeared, or if it was all gray, or didn't show up at all, because a lot of times miscellaneous hits will disappear in the velocity data. For example, we had those, there was some spurious hits down here in the reflectivity data, remember? And now they show up as, oh, well, one is green, huh? They do show up in the velocity data, which is kind of surprising. So there must be something there, because a lot of times spurious hits will just disappear in velocity. They won't even register in velocity. So this gives us an indication of where, because this one is saying rocks in the air and they're right here. So at least narrows down where you have to look. So now we can look at other radar. That's why I like to go to one of the far away radars first. Let's go back to here. So, here I look over in these radars, KEOX. Let's go look at the KEOX time frame. 4.3, and the one after 4.3 was like 413, which is not of interest, but I've probably deleted it since then. I probably downloaded it at the time and then ignored it. But let's look at this one. So once again, I look at the timestamp over here. That's 4:08. We're starting to get fairly late. So, if we look at the later scans, the 6-degree scans, and here's another reason I don't do a full volume scan. A lot of times you get out of range on some of the faraway stations and everything turns purple. That's just telling you that I can't do my range. I can't determine range beyond this purple line, where this purple line starts. So it no longer is actually measuring range anymore after that. So it just puts a big RF purple blob out there. And if you do a full volume scan, you get that purple blob. You get all that clutter of the low elevation scan, which is mostly ground clutter. It's just reflecting off the trees and bushes and rocks out in front of the radar and coming back, and it produces some range signal out of that radar return. And you get all that data if you do a full volume scan, and it overlays it on top of each other. And I try to keep my data just clear. I just want to see areas of, just single hits and hits kind of far away, so I can isolate that area and determine where the hits are first. So then as this is fairly late, it's probably things are not of interest that late. So I'm going to start, as I would march down in time, 409 starting maybe be of interest. There's a 408, which is not too bad because 405 was my time, and 408, 27 to 409 type frame. That's 4 or 5 minutes afterwards. That's getting a little late, especially for a high elevation scan. So as I keep coming down, and now we're getting hits, but they still look like just random hits. So, it's hard to say that would be, meteorites in the air, and which one, this one or this one. They're kind of far apart to be able to see. So we keep coming down to more closer to the 406 time frame. There's a 2-minute line. Now we pay more attention maybe to this hit. This hit could be potentially meteorites because the timing is right now. So I like to do time, try and load all the files that are before and after the time of interest. And then I'm really looking at only the elevation scans that produce uncluttered hits in the area of interest. So, as we back out, and these are probably radar hits now there, but once again, we're starting to be in the cluttered area. So it's hard to determine. It's like, well, are those rocks in the air? Or are these rocks in the air? Which of these is right? So it's nice to get a nice lone hit somewhere out there. Like KMX will have one. See, now we see a fairly good size hit. Again, it's kind of in a cluttered area. So as we start working our way back up, we still get a hit, and there's a lot less clutter around it. So that's more of what I'm looking for, is first to determine where it's going to be and try and say that those are rocks in the air, as opposed to just random hits. I try and avoid the cluttered areas. I try and avoid, out of range areas. And this one has a good, has some velocity on it. So, that gives me more hope or indication. So that's what I typically do is, once again, go here, I'll grab radars that are within 100 miles or so of it, 100 kilometers at least. And I do like to look at the further away stations because there's a lot less clutter on them and you're seeing things higher up. So a lot of times that higher up will, there's a lot less things up in the atmosphere higher up. So, if we look at the Atlanta scan now, it's, it's a little further away. And if we start looking at these higher elevation scans, there's nothing at the 407. But once again, I would start at a higher scan and work my way down. Boom, there's a nice big hit, all isolated. It's got more than one range bend, very typical for rocks in the air. You're seeing multiple hits, 1, 2, 3, 4, 5, 6, 7, 8, 9, like 9 range bends and 2 azimuths across there. So an azimuth here and an azimuth here. Get another one again. It's all alone. It's away from the clutter. So if you do a full volume scan, you're going to get this data here. Hold on. That data laid on top of your radar hits. So I can't see what I have at 4.4 when all this is laying on top of it. So, but as I say, you can go to the time scale slider and just look at each individual hit. But what I'd like to do is then, once I've got one of interest, then I'll just zoom in on that one. And then I use the launch KMZ here. So I go straight to the KMZ. You could save the KMZ, but I launch it and I almost always just put it on the surface. Yeah, you can catch it up in the air and look at it up in the air. And I do look at the altitude, but I do that separately. First thing I do is go put them on the ground and look at them. So see how many you can actually, you get a big scattering of those on the ground, and it's a lot easier to, then I'll from that general area, then I start wind correcting them. So then I'll go back and look at what altitude is that radar hit. And then how much wind correction will I need to apply to that. So let me go back to this tool. I think I can demonstrate this other problem too. So that's just in the same area, but it's just over here by itself. It's a smaller radar hit. So then that's when I'll start looking at their altitude and then wind correct them. This will turn out to be, I think these were wind corrected almost due east, about 1 kilometer or so. Some of the there were some higher hits over here that have never been found, in my opinion. There was a early one almost over Josh Buckner's house. And, the wind shift should have put it over here somewhere, and none have been found up there. So we wind correct it, and I look to see the timing of those hits to see what size rocks we should be talking about. So I can get the exact time of that, and I won't demonstrate that here, but it's not just this time, because that time is what time it started that whole sweep, the 4 degree sweep. So, and I don't know where it started that sweep. So here's the radar, it's in the center of that little black hole right there. And I don't know whether it started right here and that is 411, 40711, or whether it started here and that's at the very end of the hit. So I don't know if this occurs at the very beginning or the very end of that elevation scan, but I can go look at that actual altitude and timing of that one hit and then determine the size of those rocks, because if that's at 5 kilometers and the dark flight began at 4:05 exactly, and this is 2 minutes later, exactly 2 minutes later, I've fallen from 20 kilometers to 5 kilometers. Falling 15 kilometers in 2 minutes tells me the exact size of that rock. So assuming it's an ordinary chondrite, I do have to I have to assume a density and work through that, but I almost always assume an ordinary chondrite. And then I can say those are 100-gram stones or 500-gram stones or kilogram size stones in that radar hit. And then we can correct that for the wind, because I know how long it's going to take to reach from 5,000 feet down to the ground. And I can do that wind correction. If it takes it another 30 seconds and the wind's blowing at 5 kilometers per second, then it's 30 times 5 or 150 meters that you have to move that hit to put it on Google Earth. So that's how I do radar. And like I said, I actually go and look at each of these radar, and I do direct download almost from the site. So I'll show you that rather than how he did it. Let's see, 9/26 to 2022. And then I create a graph right there. So it tells me the actual mode of the radar and what it's doing. And I'll just go down here to direct download. It gives me all the scans right there. And I know it 401 and 411. So I'll might take this one, and this one. And sometimes it splits the file when it does a calibration thing. So if you download both those files, when you open the WCT tool, you'll only see one file for that time frame. It's combined those two files internally. So, but I know the 401 is almost the only one I'd be interested in here, because I calculated that 410 would be too late. If the event time is 405, that's 5 minutes afterwards. If I see any hits in this one, they're going to be at the low altitude. They're very close to it. It's going to be in the clutter. So this radar hit is of no interest to me at 411.
What is the MDM file? You said it combines those two files. What is the MDM?
It's calibration.
Okay.
Every so often it runs calibration stuff, and usually it's not that often as it's showing here, but 156, 256, 350. It's every hour. It looks like it's running it every hour, some sort of cal. But what that does is it kind of interrupts, and it like I said, if you download both those files, when you actually look in your WCT tool, you'll not see two files with the timestamp. There'll only be one. So it's taking that cal data and putting it into the same file somehow or another, when it sees them both. Or it just doesn't recognize the MDM as a radar data, and it's just a cal, and it doesn't bring it up. So, because then, here, because I save all those to, I save everything by date and where the location. So, my meteors, there's Georgia, September 26, 2022. And I only added Junction City later on. In reality, I just have, like if I go back to Georgia, it's almost all just dates, August 22nd, to boom, boom. Most of them are done purely by dates. The files there. I don't see all the radar files. I don't see the seismic data. So that's what seismic data looks like. I know we're on radar here, but that's kind of what seismic data looks like. You'll see a big sonic boom. And that one's 0.2 pascals, which is audible to the, would be pretty loud to a human ear, but.
I'm not sure we're seeing what you're talking about, Pat.
Yeah,
Oh, yeah, that's right. I'm not sharing I'm only sharing 3 of my apps. That's right. WCT, Google Earth, and Internet. Sorry. Anyhow, that's all I think I wanted to say.
all right, thank you, Pat. Turn it over to Sammer. He's going to go over some WCT tips and tricks.
All right, thanks, Jim.
Yep.
All right, we got to wait for Pat to stop sharing first. All right, Pat, if you can stop sharing so I can share.
Well, I'm trying to see how I stop sharing.
The top somewhere will show up.
Stop share. There we go.
There.
Got it.
All right, so I figure, before, pretty much Tony and Pat showed you a lot with the WCT software. And primarily, I would like to tell you that if you want to do this, you have to be patient, and you have to do some reading. Don't go into it expecting, you're going to find meteorites. I want to remind you that this software was designed to showcase weather data, rain, storms, snow, but it will catch a lot of other things. It will catch, like Pat was saying, trees, buildings, wind turbines. It will even capture birds flying in airplanes. So how do we distinguish the meteorites? And that's the big question. So a few tips here, some websites that I would like you to direct you to: weather.gov/MKX using radar. There's actually a different website. It's the Jetstream one. So this goes through what the radar does. And I think reading about what it does will help you understand what you're looking at. So to begin with, you can kind of just go through it here with how radar works. And ideally, it's sending a signal. It's reflecting off of something that it's hitting, and it's getting part of that signal back, not a big part of it, just a tiny part of it it's getting back. And that's what we're reading as the intensity. And the reflectivity data, they show you that as the decibels, right? The dBz. That's the part of the intensity that's coming back to the radar. Not all the signal comes back. And there's all the modes that Tony and Pat were talking about. That includes the velocity and so on and so forth. But this part of the website here, the volume coverage, I was doing some reading here, and it helped me understand better what these angles are that Pat and Tony were clicking on in the WCT program. And here we show you where the radar is and what the elevation means, right? So when you click on the 0.48, that's almost half a degree, and that's the 0.5 degree. And anything that's close to the ground, that's maybe 20 miles away from the radar, that's going to relatively be on the ground, right? But for things that are much further away, that's a little bit above the ground. So you're going to get some of the higher elevated particles. And I think maybe that's why Pat likes to use the farther away stations, right? Because then you'll get the higher elevations with the lower angles. But there was a peculiar thing here that I came across, and that is the clear air mode that some of the radars run in. And it can detect things like dust, bugs, and particulate matter that are very close to the radar. And I thought that was pretty peculiar. It could be meteorites, right? But definitely worth going through, taking your time, reading through a lot of these informative web pages that tell you about the radar and how it works. And ultimately to get to the point where you understand what reflectivity is and what those dBz values really mean. And I think one of the questions I asked Tony a few weeks ago was, when you look at a radar hit, and I don't have it set up here, but when you look at one of the radar hits, let's say 1 pixel, can that give you a number? Do you have a number of how many raindrops or how many meteorite drops in this case, how many meteorite rocks are up there? And I don't know what the answer to that is.
I can answer that question for you if you'd like. But
Yes.
yeah, it basically gives you a radar return. DBZ is baseline to 1 millimeter size water droplet per every cubic meter. That's what DBZ basically means. So if you're receiving 5 dB, that is in the fifth about, I gotta pull up a calculator to convert that. But it does purely radar cross section. So reflectivity is how much radar cross section I'm receiving. I sent out 1 billion watts. I received 1 watt.
Right.
Back. That is, 1 dB to me. So.
Got it. Yeah.
So 5 dB is actually a very large signature. So and this goes way beyond what anybody needs to know or possibly many people will understand, because radar is actually quite complex. I mean, this thing's pulsing hundreds of times every azimuth, and it's not stopping. It's continually going around. And when it changes elevation, it moves up a degree. It's not stopping and then moving up a degree and then starting at the same place again. It's continuous revolving. So when it moves up to the next degree, you're actually missing some data in there because you're going to miss a couple of azimuth scans. For the 1 degree scan or the 1.5 degree scan versus the 2.5 degree scan are not starting at the same azimuth. So it's not starting at exactly 0 azimuth, going all the way around to north again, and then doing the 1 degree scan, 1.5 degree scan after the happen scan. It's continuous. So the next scan will actually start about 2 degrees of azimuth, 2 to 3 degrees of azimuth later. And it sends out hundreds of pulses at each azimuth, and then it stops and listens. And that's why you see that black circle around the radar station, because it can't transmit and receive at the same time. So it transmits a whole bunch of pulses, and then it sits there and listens. So during that millisecond, it does this all in milliseconds. So during that millisecond when it's transmitting, and then it stops and listens, that's why that black ring is around there, because it can't hear anything within the first kilometer or so, because that's how long it took the radar beams traveling at the speed of light before it could turn its transmitter off and turn the receiver on. So it misses the very close-in stuff. So that's why there's a band there. And this also causes some of the artifacts that you'll see in here. Sometimes you'll see a solid purple line, all the way out on 1 azimuth. And what's happened is it got a return, and the type of return it got, the radar data, the INQ actual internal data, is twisted such that it can't get the range information properly out of it. So it doesn't know whether that was an earlier pulse or a later pulse, and it gets confused on the range equation and says, I can't determine the range. What I'm going to do is just put a radar sweep out there of all the possible ranges. And sometimes you'll see a dot, a line of radar hits with a little space in between them all the way out on 1 azimuth. Well, that is because I've messed up my range equation, but here's the possible ranges, and it'll have it every 50, every 2 kilometers, there'll be a range hit. or it'll just be a solid line all the way out saying, well, they're all valid, you know. So you get a lot of interesting hits out of that. And around mountaintops, you'll almost always get hits around mountains, and they'll be there all the time, or you know, until they run a new cal, and then it changes. But they run cals almost every scan. So when it first starts at 1.8, 1.5 degree scan, it runs a cal. So it sends out a pulse to say, what am I expecting my background radiation to look like? And then when it gets that, it does the cal and says, okay, I'm going to set my gain. So every elevation has different gains set each time. So, but yes, you can determine how many rocks are in the air in that, but it's so complicated and hard that it's almost meaningless.
Yeah.
Because I can get one, you know, in that scan volume is, say, 250 meters wide, 250 meters tall, a kilometer long, and that's 250 million square kilometers of information. If there's 1 millimeter droplet every cubic meter, then I get 0 dB out of that. But if I can get 5 dB, I'm getting 100,000 times the radar return I would get if there's a 1 millimeter drop. So basically, if you combine all those drops together and multiply that by 100 million or 100,000, and that's how big the radar, the rock should be. And that could be, okay, does that mean I've got 1 5-kilogram rock, or does that mean I've got 100 10-gram rocks? Because there's a correlation, and it's n to the d to the 6th, the diameter of the rocks to the 6th power, and the number of rocks, a ratio that you can calculate that, okay, these are 100-gram stones, so there'll be 10,000 of them in this volume, or 50 of them in this volume. 10,000 probably unrealistic. 50 of them in this volume scan. So there is a way to do it. It's quite complex. I have not even perfected it yet, and I've been trying for a couple of years. I've got a K factor in there, but basically it's the number of stones times the diameter to the 6th power, and that gives you a radar return, a magnitude of return. And then it's in decibels, so you have to convert it back to non-decibels by raising 10 to the 6th. But you get the equivalent of 1 millimeter drops versus what you're getting. So if you get a 20 dB return, that's huge.
Got it. That was good. Yeah, thank you for that.
But to me, that's data that goes way beyond what anybody needs to know, because you know nobody's going to really try and do that. They're, you know, once you see red and green, you run, you go look for rocks.
Yeah, exactly.
You don't care how many rocks there are. I'm gonna find as many as I can find. You know, I'm not going to
forgive
say,
my scientific curiosity, because that's sort of what I want to know. Oh, there's a hit.
550 rocks in that volume scan. I'm going to stay on the ground until I find all 550. But you know, if I found 550, then I would not stop. I would say, well, maybe there's more.
Yeah, exactly.
So, but yeah, it's complicated. It's possible, but I have yet to find real value in that.
Yeah. All right.
Makes sense.
Yeah.
Quick question, Sammer.
Yes.
On one of the pages you were showing, it showed the radar beam curving up. I was wondering, did you see that?
Yes.
Yes,
Is
it
that-
does.
Is that because of the curvature of the Earth, or is that the refraction of the atmosphere?
It's refraction of the atmosphere.
Okay. Oh yeah, there it shows refraction. Okay. I saw a different picture where it showed, I thought it was curving up, but anyway.
And there's different modes, as he says, the VCPs. There's, you know, VCP 32, 232, things like that. I love the VCP. It's actually a bad weather VCP, but it goes really high altitude. It goes to 19 degrees, which I love because, you know, it's sampling air at 70 kilometers altitude. I mean, that's like when most of our meteors are just starting to glow.
Yeah,
So
there's the picture.
it can catch them up in the upper, you know, when they're still in light flight, when they're still visible. I love those modes, but you don't see them too often.
So is it refracting here then, you were saying? Is that why it curves up as it gets further away? Actually, the other picture showed it curving down, I thought, but.
Yeah, well, it can curve down too. Curving down is called super refraction. It's in there somewhere.
Okay, so it depends on the atmospheric conditions, which way it.
Yeah,
curves.
depends on the temperature of the local
Yeah.
atmosphere. Super refraction would typically be in a thermal layer.
Okay,
That's the ducting here.
There's
So
super refraction right there. Bends
Yeah,
more
there's-
than normal, but it's
Yep.
down.
okay,
cool.
interesting.
But
Yeah.
in general, you can, the radar will tell you at the altitude of the radar hits. You can actually export that and it'll tell you the altitude that it saw those radar hits.
Well, it's good information for me to know that it can refract like that though, because it means there's more to the measurement error than I previously thought, right? I can't
Well-
exactly locate meteorites, and it might explain why, like I was showing that trajectory earlier, and the trajectory didn't exactly match the hits. So maybe it's because of refraction. Because that's not predicted. That's not part of the product that comes out of the data.
It's not part of the product, but it is, I mean, it will put the meteorites in the right spot. I mean, you're seeing where the meteorites are.
Well, the data analysis or the automated analysis doesn't know the atmospheric conditions, right? So it's showing you where they should be if there was no refraction or if some standard refraction, right?
Well,
That
that's
is,
a good Steve question, but I
yeah,
think
yes,
it does determine some of that when it runs a cal.
Oh,
Yeah, I think Steve was saying something.
yeah, no, that's correct. It assumes, I'm looking up the equation. It does not take anything into account that would compensate for atmospheric conditions that changes refraction.
okay.
At least in
Good.
these level 2 data. I don't think they do in the level 3 data either.
What does the calibration calibrate against? That wouldn't have any way of knowing the altitude of a hit, would it? I mean, recalibrating against ground objects?
No, but if it gets a reflection off of a thermal layer,
Mhm.
you know, it will take that into consideration and put the gains lower so that it would lower the magnitude of the hits you get because it's getting hits back. You know, it's getting data back when it thinks it shouldn't. So
Just adjusting the gain. Okay.
yeah, and especially important on the lower levels when it's getting a lot of ground clutter. You know, it sees a lot of ground clutter and says, well, I don't want to, you know, have 400 dB coming in at me. So I'm, you know, if I'm bouncing off a building that's only half a kilometer away from me and I'm getting all this data back on that azimuth, I've got to stop looking there. You know, I'm going to look farther. I'm not going to run that. Or if I run that, I'm going to have to turn my gains way down so that I can see things past that.
Yeah. Okay, that makes sense.
All right. Shall I continue then?
Yeah, go ahead, Samer. Thank you.
Right. I think a good place for any beginners to start is with the Mark Freese website from NASA here. And I'll, you know, there's the link over there. The Astromaterials Research and Exploration Science Meteorite Falls, how to find meteorites. It was updated, you know, a few years ago. but it's got a very good step-by-step process for anyone that's interested in, using this tool to find meteorite falls. And, Mark goes through the whole spiel of how to use the different products in the tool. And it includes, downloading it, listing the data like Tony was showing you, and then pretty much doing what Tony and I and Pat, Pat does it a little bit different by downloading the data, but essentially it's a tutorial for the WCT tool. Now, let's see here. Before you blindly go into the tool, you want to go to the AMS website and get a general idea about where the meteor happened, right? And in the case of the Hamburg meteorite, the AMS website showed us that it's somewhere north of Brighton, Michigan, but the radar hits were much south of that. They were about right here. So another case where, the AMS website relies on people reporting where they saw the meteor in the sky. And that gives them a very, very close, sometimes quite close estimation of where that happened. So now you go into the tool and you want to zoom in on that area. Now don't zoom in too far, and zoom in just enough so that you can get the general area. Now, some people quickly go straight to the streets view so that you can see the names of the cities and the towns and where you are. But it's suggested that you start with the dark because the radar hits that are anomalous can be seen immediately. And when you go to the data and you want to load the data, right? So there's the date, you choose the date. In this case, it was in UTC, January 17th, 2018. We're going to choose the KDTX and list the files. That's the station. And then, the time, it was about 1:08. So we'll choose a time before and a time after. But for now, let's just choose this time and let's just go load. And a lot of noise will appear. Not sure what happened there. Oopsies. Let's try that again. Color parameter outside of expected range. Well, maybe it's malfunctioning.
Yep, you have to reboot. You have to reload the tool. I had that going yesterday, and reloading it, like relaunching the whole tool, was the only fix.
Well, it's not always easy to work with these things.
Yep. That happened to me, Sammer.
All right. I'll save you
Same note.
time. Pretty much
Color
what you
range.
need to do is just look at the AMS, see where the general trajectory is, zoom in on that region and see if you get any radar hits close to that region, but keep an open mind. Don't just focus on that region. Keep an open mind because it could be several miles northwest, east, or south of that. And then if you get something peculiar, then you go in and you change the time to go to the sweep before the fireball or the meteor happened. And if those hits are still there before, then they're not the meteorites, they're something else.
Mm-hmm.
And if they stay way after, then there's something permanent that's always there, and you just want to ignore them. You're looking for things that appear and disappear in the time frame, in the time sweep of the meteor fall. So if it appears and then disappears immediately after, then most likely that's the meteorites that you're seeing in the atmosphere there.
Keeping in mind that the sweep time is the time when the sweep began, right? So it can be, what's the sweep length, Pat? 20 seconds or?
It depends on the mode.
Yeah, okay,
It can be as short as 20 seconds, as long as a minute.
right.
Actually, it could probably be a little less than 20 seconds, but yeah. Depends on the VCP mode.
So the sweep time could possibly be before the vent time, but not by much.
Yeah, and then finally, if you really want to master this tool, then go through the tutorial and see all the advanced ways in which you might be able to use it. But definitely, what Mark Fries has is a wonderful start. Go through it step by step, and then practice. It's gonna have to be patient. You cannot find these things immediately. You have to be patient and download a lot of data and spend some time looking around. Use a different station that's a little bit further away. So yeah, that's sort of what I had.
Which is why we wanted to have this workshop, right? So we can get a lot of people trained, because these meteors are coming faster than we can process the data. Some days.
Can I ask a question at this
Yeah,
point?
let's start the Q&A.
So to ask my question, I'm going to share the screen because it's going to be hard without that. And this is to Samer's earlier point that he made. Share. So can everyone see my screen?
Yes.
Yes.
Okay, so we have the Hamburg hits, 443 sweep. We found 2 meteorites on this lake, all of 2 very small meteorites on this lake, but note the gigantic hit. So this is getting to, and it's really like 2 blocks of data. One is here and one is here. So does this block represent a margin of error? So we were talking about
it's scanning. It's scanning a volume, and that's where we talk. Each of these blocks is a big volume. It's 100 million, cubic meters of volume. It's 250 meters wide, 1,000 meters long. It's a half a degree.
Okay.
It's a degree
Right.
in azimuth wide. It's a degree in altitude.
Right.
Yeah.
Okay. Thank you. That answers the question.
And there could be one rock in the middle of that whole entire volume that gives you 5 dB, or there could be 100 small rocks in that area. So you
right.
don't know unless you're getting down into the timing of everything and the size of the rocks they are, and it involves a lot more than.
Yeah. Well,
But that's
we
the resolution too, right? So it could be one rock on the edge of that block somewhere too, right?
Correct. And it does do some averaging between the 2 hits. If you go over to the middle hits there, where it's a dark one and a light one next to you, right there, those 2 hits, those 2. Now it could be that the rock is just barely in the darker hit over here.
Okay.
And that if you right close to the edge, but just in the darker side. Now it's picked up in both scans because there's a little bit of overlap. It averages the data from, I can't remember what it is, but basically a quarter of a degree overlap on the azimuth.
Okay.
Or is it
It's a volume.
250 feet in? Maybe it's in range. I'm sorry. Maybe it's in range. It's 1,000 meters in range, but you're really getting 250 meters averaged before or after in there. So there is some overlap, and that could be that there's only one, even though there's 2 hits produced right there, it could be that there's just one rock in one of those 2 hits, and that there's some bleed over to the other hit that causes it to get some dB return.
Pat, why would it be negative?
Because you can have negative dB. It's dB, remember, to 1 millimeter. So it's basically saying 0 dB is 1 millimeter per every cubic meters. And if you have 1 million cubic meters of space you're looking at, then if you only have 100 gram rock, it's probably not going to be equal to a 1 millimeter, a million 1 millimeter droplets. Probably will be about the same, but yeah, a single small stone would be a -5, -10 dB.
Okay, so just repeating what you said to make sure I understand, this is a volume,
Well, that's two
Or-
volumes
or-
next to each other.
two volumes next to
That's
each
two
other.
separate, yeah,
Yeah.
that's two separate
Okay.
pieces of radar data in the INQ world.
Okay, so a single square here that we're looking at is one volume.
Right.
And let's just say these two volumes together represent an area or two areas that have produced a return somewhere in that area. Is there, and there's no, we were talking about maybe getting, finding a way, Pat, you were saying there might be a way that you've been researching
Oh, there is a
to get
way.
more
That's
to get more
known
precise
equation.
as to where the individual rocks that produced these two hits within this volume might be. But really, this was, I think, a good example over here on Hamburg Lake, because it's I mean, I know we trampled this whole lake and we found two very small rocks. It's a good real world example of how this very large volume can be represented in terms of rocks. Now, there could have been dust that we didn't find, I know, but we searched pretty hard on that lake, and it wasn't only me. There were a bunch of people out there trampling it, and only two rocks came back.
I'm sure there's lots you didn't find, but yeah, it's, you know, that's the same equation. That's the same confusion with Oklahoma. You know, we found 6 stones total have been found, no small ones. 70 gram was the smallest one, and yet here's 400 radar hits scattered over a couple of miles.
Yeah.
And like, what's producing those radar hits? There's got to be stones there. There's got
There's
to be some
gotta be
10
right.
grammars. There's got to be some 5 grammars. But we didn't
Yeah.
find any. That doesn't mean they're not there. They're there.
Yeah.
We just didn't
Okay.
find them.
Roger that. Yeah, that was just my question.
And
These,
Tony, both of those hits, sorry, I think I
Go ahead.
dropped you, but yeah, both of those hits include some land, right? So maybe they
Yeah.
weren't on the lake, maybe they're
yeah,
on the
they
land.
could have been over here on the land. It could be anywhere in that volume.
And you got to correct that for wind. So
And this is up in the, that's right. I was
Yep.
just gonna say that. This is way up in the air, and the wind would have moved them, but oddly enough, the hit is right over where we found them. And it's not over where we didn't find them. You know, nobody found rocks here. Nobody found rocks here. I think the wind was blowing this way, but we haven't
it's-
found anything there. But we
it's
did
more
find some
likely
over
that-
here, though, in this park.
it's more likely the stones you did find were probably over here down to the south, and they just weren't picked up on radar.
Mhm.
You know, those that were picked up on radar are still over there by that curve in the road, and that's where you should be looking for those hits, those radar
Mhm.
hits.
Over here.
Ones you
yeah.
found on Hamburg, yeah. You know, these might
Well,
be over there because 4 degrees is
I'm
pretty
gonna-
far away, pretty high altitude. I don't know how far away the radar is, but
It's a
the
little long after this fall, but I'm actually gonna go hunting there this spring.
yeah, the radar hits, and I don't know what the wind correction was. I vaguely remember Hamburg because I remember sending somebody to Strawberry Lake, and
Yeah.
but you know, whatever hits were found on Hamburg, or you know, Hamburg Lake, it's probably right about where, oh, that's my cursor. Somewhere down to the south there, southwest, probably even a little further, you know, but yeah,
West over here.
maybe over by this other little lake,
Way over
halfway
here.
between those two areas you just showed. Now the middle of the screen lake. Yeah, just go underneath that point,
Here.
that right there, yeah. Maybe that is where the radar, where the rocks were at 4.4 degrees,
Oh, yeah.
and they blew over to Hamburg Lake. They just weren't picked up on radar.
Mm-hmm. Right.
Recognize
Follow-up
that
question.
minus 10 degrees is minus 10 dB is pretty small return.
Mhm. Yeah, I have a question on the dB values in terms of meteorite signatures. If we see it in the greens and the yellows and the red, should we even bother suspecting that's a meteorite, or those are meteors, or should we?
Not likely. I
Mhm.
mean,
Has there been
we have
any
yet
records
to
of
see
that?
something that big. Well, I'm sure the main mass of Chelly would have produced something in the 50 to 60 dB range, but in general, you're probably not going to. Ash Creek was probably the heaviest concentration of things caught on radar before, so I would be surprised if you ever see anything bigger than whatever Ash Creek produced. And I think there might have been a couple of greens, but in general,
You're looking for these blues, the grays and the blues.
yeah, you're looking for blues mostly.
Okay.
Because rock should produce more than 1 millimeter droplet of water. You know, if it's a decent sized fall.
And once again, why are these down in the grays? Negative area?
Minus 10 dB.
Yeah, why is
Minus
that
10
again?
dB means it's minus 10 dB means it's 1,000th of what it. Hold on, I have to pull up a calculator again for that.
A very small fraction of a return from what was sent out, right? In the radar scan.
Yeah, it's a millionth of, no, not just
No?
a fraction of a small return. Yeah, that is how much radar energy is returned,
Mm-hmm.
but recognize that it is the Z means the baseline standard it is using is 1 millimeter droplet every cubic meter in that volume.
Millimeter droplet every cubic meter. Z equals 1 millimeter droplet
Every cubic meter.
per.
So you take all that volume that it was scanned, and let's say that's 100 million cubic meters of volume, and 100 million 1 millimeter droplets. Put all those together into a ball. How big of a ball are you looking at? That is what 0 dB should represent.
Okay. That'd be a bigger ball than the rocks we found there, I can tell you that.
Not at
that's
minus
why
10
and that's
dB.
why
I'm
we're
saying
negative.
0
So, right.
dB. Yeah, that's what 0 dB would represent. Minus
Yeah.
10 dB is
Yeah.
1/10 billionth or 1/10 millionth of the droplets.
Yeah,
So
okay.
basically you're looking at 1 millimeter size meteorites at minus 10 dB. So
Right. And they were small. I mean, the largest one on Hamburg Lake was only 1 gram. It was not even 10 millimeters in size. And the one my daughter found was smaller than that.
Right.
It was not even a 1/4 gram in size. So
that's why it's just easier to use
size of a Rice
timing.
Krispie.
That's why it's easier to use timing and say, okay, this sweep occurred at 1:16:30. The event time was 1:10:30. So this was 6 minutes afterwards, and that represents 10 gram stones or 1 gram stone. Those are 1 gram meteorites in that volume scan. So that's all I care about. I don't care how many of them there are, but there is a way to determine how many there are by ND to the 6th power. So
yeah, so 1 gram, that was that was Brian Barnamo's rock. It was like 1 gram. It wasn't,
Yeah.
I think I may have said 10 grams. I meant 1 gram. And then my daughter's rock was a 1/4 gram. So they're pretty tiny rocks.
Yeah, generally I would stick to
That's
the
why the,
bigger end. I would stick to the bigger end of the Strewnfield
Oh,
radar hits
oh,
until,
of course.
they're all
I would've-
exhausted.
Yep, no, we had already done that, and we have
Yeah.
found bigger rocks over, we found other rocks on Strawberry Lake, but this was now 4 days after the fall, and, you know.
Yeah, as you get much
up here
later
by-
in
by
time,
Strawberry and Bass Lake, it was all searched out, and so we turned our
yeah,
attention.
you get
to
much
those
later in
smaller
time,
rocks.
you're talking about smaller and smaller rocks on the radar hits. You get later and later. You talk 6 minutes after the event, and you're
Okay, so-
talking 1 gram size stones.
Let's go now to the larger rocks. So here, and then here. Now over here, we were finding, you know, this is where I found mine. Right about where the
Yeah, and this is
Fingers
2.5
did.
minutes earlier. 2.5
Yes.
minutes earlier is
earlier, but it's
quite
still
a
the same
bit.
color. It's still this, here's the question. It's
the
still
color doesn't
same
matter.
color?
The
Okay,
timing matters there.
timing, okay. So look at
Alright.
the timing.
So you've got a color, and what I'll say is
Still negative though.
one rock, that doesn't matter. One big rock can produce -5, 0, 5. You know, one rock can produce any of those things. -5, 0, 5. Let's say one
And the
rock
idea
can
with-
produce that.
And the idea with the time is that
5 rocks could produce 5, 0, 5, you know, -5, 0, 5. You could have 5 rocks in that volume. You don't know how many rocks are in that volume. Just
Mhm.
because it is 5 dB doesn't mean it's one rock. It doesn't mean it's 20 rocks. It doesn't tell you how many rocks there are.
Gotcha.
The color does not tell you how many rocks are in there. All it tells you is I've got 5 dB of return. It could be one rock. It could be nd to the 6th power rocks.
Mm-hmm.
You don't know how many rocks are in the volume. That's why I say just go straight by timing. That sweep is 2.5 minutes earlier. 2.5 minutes is, let me go pull off my chart here. For spherical meteorites, two and a half meters is more than a factor of 10. You know, it's the difference between a 1 gram stone and a 10 gram stone.
There you go.
Or it's the difference between a 10 gram stone and a 10 kilogram stone.
Well, that's really
Because-
amazing because
Yeah,
over here we had 1 gram and over here we had 10 to 16 grams. And then over here, which is a totally different hit, that was more in the 20 gram, 26 gram range. And they found many bigger ones. This is really the honey hole over here and then over here. But in this part of the lake, we were finding 10 to 16 gram rocks.
Right. And if you tell me what time the event actually, you said right there you're finding 10 gram stones. I'll tell you what time. Let's assume that 1:14:05 was the exact time of this. Probably isn't, but 1:14:05, and you're finding 10 gram stones. Then I would say that event time was 1:11:20 roughly. What time? What's the exact time of that
108,
fall?
108:31.
108? Wow.
Yeah,
They're even
yep.
smaller then.
Oh. Well, here now
Well,
it is.
I don't know what altitude that radar hit is. exactly, but I was just taking 5 kilometer altitude.
The next elevation down is 248. We were
Yeah,
looking
but
at
I don't know what
249.
I don't know
And
how
now-
far away you are from the radar.
Yeah, and now it is 112.53. And we're getting
Right.
even more hits over here.
Right.
I don't
See,
know,
but
I'm
now you're a
just-
whole minute earlier. You're a whole minute
Yeah,
earlier
a whole
now.
minute earlier. But these hits are still here, strangely.
Yeah, exactly.
Why do they linger? If
They're
you're a
bigger
whole minute earlier?
stones.
Okay,
They're bigger
So-
stones.
so it picked up the same stones twice?
No. Well, it might have, but not a minute later. It shouldn't have.
It's
Yeah,
about 40,
Fall
40
through that
kilometers.
time.
from the-
Watch this, here's 249. And then I'm loading it. We'll let it load, and that's 114.05. Okay, so then we
Right.
go to the next, the one,
Those are smaller stones coming down a little later.
okay,
The bigger stones in the 248, the first 248 scan, slightly bigger stones in the 248 scan.
but they're
And
coming
yes.
down in that same volume, correct?
They're coming down in the same general area.
Okay,
Not a problem.
okay, yeah, I guess that can happen, right? Sure, of
Yep.
course. All right,
They're just falling, but
then-
the
and then we
stones
go
that
to the
fell
earlier-
through,
the earlier volume scans, they again produced hits here. They're different looking, but
Yep.
still in the same volume, but earlier rocks.
and being slightly larger rocks, you'd expect maybe a little more reflectivity, but that's not necessarily given because there could be more of the smaller rocks producing a bigger return than fewer of the bigger rocks.
Or the bigger rocks. That makes sense.
And over here to the left, you're getting,
Mhm.
some blues over there, but you're probably talking a lot bigger rocks and a lot
Yeah,
fewer of them. So you're talking 100-gram
over
rocks
here-
over there. Those are 100-gram
Yeah.
rocks.
right. And that's correct. Because right here was the 138 gram specimen that was found. And I'm not sure where Robert Ward found his, but I think it was here on Bass Lake somewhere.
Yeah, it was on Bass, if I remember right.
Yeah.
I remember talking to him about there were hits on Strawberry and hits on Bass that I was sending him
Yeah,
to. But
so that's where the bigger ones were, indeed. Okay,
but the timing roughly tells you what size rocks you're seeing on those radar hits. That's why I like to go to the timing part of it and say, okay, those should be about 100-gram rocks. Those should be about 10-gram rocks. That should be a kilogram rock. Let's go find the big mass.
and oddly enough, now it's 111.40. No more hits showing up, even though this is still 3 minutes after the fall, after the reports, right? But they still,
Yeah,
but
but-
at 3 minutes after the reports,
You're also
didn't
a lower altitude.
lower, yeah, it could be
So-
missing them, so they would have been up higher.
They could be up higher in the air at the time
Yeah.
that you're scanning that volume.
Yeah,
And that's how radars can miss them completely, is, they're scanning the volume underneath and while they're up above, and then it goes up the next higher one. Well, they've already fallen through that altitude and they're down below the radar when it does the next higher sweep.
yeah,
It happens, especially with 1 minute VCPs. I mean, this is a very long DCP. That's a minute between each elevation. That's a long time.
that's the
And
long.
some
time.
of them are, like I said, less than 20 seconds in elevation. It goes all the way around in less than 20
Yeah.
seconds. So
So a DPC is a cycle of the. is that-
VCP, yeah, is all these added together. No, VCP is what mode it's in. But
DCP.
yeah, a volume scan, they call all these together, all these elevations together, this one whole VCP is your 107 up at the top. That's your VCP start time. And then that's the mode, is the VCP number is the mode.
Yeah, okay,
VCP 31,
VCP 31. Yeah, that's the mode.
31 is the mode. 31 is a very clear air mode, and it's concentrating a lot to get, a lot of data. So it goes very slow, sends out a lot of pulses, 1,000 pulses on each azimuth, versus 100 pulses on an azimuth. So it's sending out 1,000 pulses before it, as it's moving around. So it's collecting a lot more data, a lot better resolution.
All right, thanks.
I need to get all this programmed into Strewnlab. I could have this tell you exactly where to look. It'd be cool
That's
to
what
see.
we already do with the radar hits. Go look
No,
under the radar
I mean,
hits.
No, I mean, I
100
could
damn
have it.
stone.
Yeah, that's the ones where it's easy, but the ones where we don't see anything or we don't see anything where it should be, I could tell like what we might have missed, or by tracking the azimuth where it's looking at what time and what angles, you could tell what data is missing. I don't know. There's a lot of cool stuff you could do with this. And I didn't know the CSVs contained all the polygons. That's pretty cool. That we were looking at that the other day. That's
yeah. When you export it, you actually get the DB reading too, rather than trying to interpret a color. It's like, well, is that color 5 or 0? It's it actually tells you it's 3.2
right
dB. So you can then take that number, put it back to the ND to the 6 and say, oh, that represents, since I know it's roughly 10 gram stones, I can go back and say this should be 200 rocks in that volume scan.
Right. By the timing, what size, and then you can calculate.
Timing, I get the size,
Basically
and then
the
I can
mass.
technically get the number by the radar cross section return.
Okay.
This could be a Steve question. I don't know if we have time still, Jim.
Yeah, go ahead.
Or maybe Pat, would there be a VCP configuration or mode that's most ideal for meteorites?
Yeah. It's the bad weather one, because it's
121.
looking for hail and ice, and meteorites look like hail and ice, or sleet covered, rain covered sleet.
Okay.
Looks like rain covered sleet. In fact, if you look at the hygrometer classification, the radar in the level 3 data gives a classification what it thinks those radar hits are. It'll say it's biological, it's ice, it's rain, it's it's hail, it's sleet, or rain covered sleet. It tries and tells you what it is by the radar return it's getting, and it really gets down in the nitty gritty in the INQ data, the actual data that it's getting back to try and determine that. But it'll almost always classify a meteorite as hail, ice, sleet covered, rain covered sleet. Sometimes it classifies them as biological because of the turbulence, but it looks like rain covered sleet. A rock by itself, a meteorite or rock, looks like rain covered sleet.
And I can't remember where we were having that conversation. It might have been on Discord, but there was I was asking if hail spikes could show up for large meteorites, or meteorites can create hail spikes. Is that possible or no? You know what I mean by hail spikes, the radar
I'm not
product.
sure what a hail spike, yeah.
Oh, so in hail, and sometimes in large hail, there can be a reflection off the ground. So the radar goes to the hail, goes to the ground and back up and back to the radar. So it looks like it's further away than it is.
Yeah,
So
that's where it gets messed up on the range. Yeah, and
Right.
meteorites will do that too, especially an iron with a lot of remiglyphs, with a lot of thumbprints on it.
Yeah.
Those irons, they act as corner reflectors, and they'll confuse the heck out of the range equation. It'll do the same thing. It'll create a spike, and that's what I said. A lot of times, if you got a large size iron, you'll see that spike all the way down. You'll see a whole bunch of returns all the way down one azimuth line, because those Remiglas messed up the range equation. It says, oh, I don't know if it's, 100 kilometers away from me or 110 kilometers away from me. So I'll just put a spike at 90, 100, 110, 120. I'll just put a spike everywhere. Yeah.
Yeah, that might be something to look for when we have large meteorites.
I do. Yeah.
Yeah.
Looking for sometimes those spikes going out is, hey, that's interesting, and I'll jump on those because, a meteorite can easily cause that. And then I'd probably be calling it iron too.
Is there a picture of what these spikes look like? Because I don't know what you guys are talking about.
Let me
There,
see if I can
an
find
example you can show?
I used
Yeah.
to think I saw one in the Hamburg data, but I think it's actually turned the opposite direction than what I think.
There was one in the recent Nevada fall, I think, the Arizona, one at the corner of Arizona, Nevada. Flagstaff produces one a lot of times. Flagstaff will produce.
Let me share. I'll show just Wikipedia's version of it here. There's a hail spike, so that's what happens. So the reflection from the wet ground makes the range of the hail appear further away than it is, and it shows up.
Are you
Actually,
showing
I'm
anything?
not
I
quite
don't
sure what
see
it's
it.
pointing at here. Oh, you can't see
Yeah,
it.
no, you're
I
not
don't see
sharing.
anything.
Sorry, just a second. Oh, I always do that for some reason here. No, don't hit the share button. Okay.
Now I see something.
Yeah, so I'm actually not sure what it's pointing at here in this picture. Maybe you can tell me. Is it this large thing here? Is a
That's
hail
the hail
spike?
spike. Yeah.
All of this, I guess.
Yeah. Because I
Yeah.
think the hail is the pink.
Okay. Yeah. Okay. So done. Okay.
Yep.
Yeah,
and
it's
there's-
where it gets confused on the range equation.
Right.
Okay.
And it
And
shows
so
here
that's
what
that
what
thing the
happens
arrow's
when-
pointing to is a hail spike. So it's a
Yeah,
spike
yeah.
that comes off of the hail.
Yeah, it means the hail was up here somewhere, and it thinks it was way out here because of this phenomenon, right? The radar hits it, and then it goes down to the ground, back up, and back to the receiver. Yeah. So it thinks it
Yeah.
was way out here. Yeah.
What I was going to show is
Reflection
going to
from
be
the
something
wet
different,
ground.
but
Okay.
Okay, that's crazy.
And
a lot of times you'll see it as a,
here, I'll show the
that's a
picture
weird-
from Hamburg. This is what I used to think was a hail spike, but I realized I think this is from a different. The azimuth is probably this direction, right? I don't know.
yeah, that's
Yeah,
not a
so-
hail spike.
No, that's not a hail spike. But I used to
Well-
say, hey, but maybe there's a big one out here, but no.
What I'm thinking is not even what I wouldn't even call it a hail spike as much as I would call it a
Go ahead and share.
range confusion spike.
Okay,
Do you have something that you were going to share, Pat?
I was trying to look for what I was
Okay.
thinking what you were talking about. I know Flagstaff equation or Flagstaff radar produces a lot of times because a lot of mountains will do it. Mountains will do it a lot of times.
Okay. Well, we're-
Ground clutter will sometimes do it.
You're talking
certain-
about the anomalous propagation.
I don't know what you call anomalous propagation, but yeah, just a line of hits,
It's this
all the way
one.
out on an azimuth.
So on my screen here, they talk about how this line right there,
Yeah.
that it, when you compare it to the topographic map or the terrain map. Okay, so this is not a hit, this is just the terrain.
Yeah,
And the hits are
yeah,
matching.
mountains will produce that, right? Mountains will produce that. But a lot of times it'll mess up the range too, especially rugged mountain.
Mhm.
I was trying to look for one. I know I got an example somewhere in the world I know I saved, but
Well, because it's basically an echo, right? Anytime it bounces around and comes back with a totally.
Well,
different
it
range.
messes up the Doppler enough that it doesn't know whether it was off a earlier pulse or later pulse. You know, because it
Oh.
kind of encodes each pulse and then says, oh, this pulse went out at, this millisecond and I received it at this millisecond. So the range must be this, times the speed of light. And in reality, it bounced off 3 other things and took a long route to get back. And, it's really not that far away, but it looks far away because it got multipath reflection. Or in the case of mountains, a lot of times it'll invert the signal and it'll think it's off a different return, and you'll get just a line of data. And I wish I had saved it so I knew where it was, but
All right, folks, I think I need to get going here. Got a few things to take care of tonight.
Yeah, but we're about 10 minutes over, so let's
All right.
go ahead and end it there for everybody. Thanks a lot for joining, everyone. This was great.
Thanks for doing it, Jim, and it's very helpful.
Yeah, and thank you, Pat. Thank you, Jim. Steve, thank you for being with us tonight too.
Yeah.
Everyone else.
all right.
Yeah.
Next time, aerodynamics. All right. Talk
We
to you
can do
guys
that.
later.
Thanks.
Bye,
Bye.
everyone.